In this video we're going to learn all about calculations of molarity and concentration. When you consider these two terms, you need to be thinking about solutions, as both of them are basically words to describe how much of a dissolvable substance, that's a solute, is present in the liquid the chemicals are dissolved in, that's the solvent. In case you're wondering why it's important to know the concentration or molarity of a solution, think about this example. Imagine a chemical factory. It carries out reactions which produce poisonous cadmium metal ions dissolved in water. It pumps the waste from these reactions into a local river and regularly checks the cadmium concentration in its waste pipe. If this concentration stays below a certain level, the cadmium isn't dangerous. But if the concentration rises above this safe level, the company could potentially be causing harm to water plants, fish, and even you if you happen to live downstream. It would immediately have to stop the reaction happening and investigate. First, let's consider the difference between these two terms. A lot of people, even scientists who should know better, tend to use the words molarity and concentration interchangeably, but this is a mistake. The difference is down to the units. When we're describing the molarity of a solution, we always mean the number of moles of solute per decimeter cubed of solution. You'll often see it written like this, or more simply like this. A cubic decimeter is also commonly called 1 litre. Concentration, on the other hand, can be written in these terms, but there are also a lot of other units popular in science to describe concentration. Here are just a few. You'll get to learn how to convert between all these units as you progress as a chemist, but let's keep things simple for now and stick with moles per decimeter cubed. You'll be pleased to know that the equation to calculate molarity is very easy. Molarity of a solution is equal to moles of solute dissolved divided by volume of solution in decimeters cubed. In this rather large beaker, which contains 2 decimeters cubed of solution, has been added 4 moles of sulfuric acid. Four moles divided by 2 decimeters cubed equals 2 moles per decimeter cubed, or you'll often hear chemists say 2 molar. Simple, isn't it? So how about this one? 0.25 moles of silver nitrate have been dissolved in 0.075 decimeters cubed of water. What's the molarity here? Pause, calculate, and resume. 0.25 divided by 0.075 equals 3.3 moles per decimeter cubed. Remember to write your answer to the right level of precision using 2 significant figures. Now try this one. 0.0100 moles of oxalic acid have been added to 100 centimeters cubed of water. There are 1000 cubic centimeters in a cubic decimeter. Pause, calculate, and then resume. First divide 100 centimeters cubed by 1000 to get the volume in decimeters cubed, 0.100. Then 0.0100 moles divided by 0.100 decimeters cubed equals 0.100 moles per decimeter cubed. Okay, a tough challenge to finish. You've dissolved 0.0748 grams of sodium bromide salt in 25.0 centimeters cubed of water. What's the molarity? Now don't panic. Simply use this equation, which lets you convert mass into moles, and use your periodic table to find the molar ratio of sodium bromide. Pause, calculate, and resume. So, molar mass of sodium bromide is 23 plus 79 equals 102 grams per mole. 0.0748 divided by 102 equals 7.33 times 10 to the minus 4 moles. 25 divided by 1000 equals 0.025 decimeters cubed. Finally, 7.33 times 10 to the minus 4 divided by 0.0250 equals 2.93 times 10 to the minus 2 moles per decimeters cubed. Very well done if you got that one right.